Hello, everybody. In this video, we continue our discussion of implementing neural networks by looking at factors that impact performance, such as depth, width, and activation functions. We also discussed the functional API, which gives you much more flexibility to create neural networks with multiple input types, non-sequential architectures, and so on. So what is the network depth? The depth of a network corresponds to the number of hidden layers that we have between the input and output layers. Similarly, we can define the width of a network, which corresponds to the number of neurons or units per layer. Typically, when you increase the depth and width of a network because you are using more nonlinearities through the data transformation, you expect to find networks that are more expressive, meaning that they are capable of extracting more complex patterns. However, in reality, what you want to do is to balance the expressiveness, computational efficiency with regards to the complexity of the data set that you have. Meaning that if you want to solve a linear classification problem where you can find linear decision boundaries to separate classes, you don't really need large values of depth and width, right? And a simple logistic regression can probably work very well in this scenario. However, if you have complex patterns in your data, meaning that the classes that you want to correctly predict, they cannot be separated using linear decision boundaries, then you want to tune the depth and width of your network. Another important factor that we have to tune is the choice of activation functions. So the activation functions are the most important parts in terms of introducing nonlinearities into the network. And we have various choices such as the rectify linear unit function, hyperbolic tangent, sigmoid function, exponential linear unit. So we have a very comprehensive list of activation functions. And therefore, it is very important to understand the impact of these activation functions on the network or model performance. And something that we're going to talk about in this lecture, which is like one of those more modern aspects of neural networks, is introducing the idea of adaptive activation function. So the term adaptive can be a little bit misleading because what we are really trying to do is to have activation functions that they have trainable parameters, right? Meaning that we parameterize our activation functions, and we want to learn those parameters throughout the training process. And this is helpful because we are not just limited to fixed shape activation functions. However, as you'll see in this video, adaptive activation functions are definitely a little bit more complicated to define because you have to specifically tell TensorFlow and Keras which parameters are trainable and at the same time be able to integrate through the training process. And all these things mean that we really need to perform hyperparameter optimization when working with neural network models. So this is something we have seen with classical models in scikit-learn, and we use grid search CV. So there is definitely a need to define tools similar to that. And in this video, we take a very simple approach and we define a grid search, meaning that we define the search space for multiple parameters, let's say learning rate or the number of hidden layers, regularization strength, and we go through all of them to see which one is the best. But there are also techniques that we can avoid a full grid search to have more computational efficiency, and we have a future lecture and video on that topic. And then the final thing that we're going to cover in this video is this idea of or concept of functional API. So what we have covered so far is sequential API, meaning that all the hidden layers that we have in our model that are placed right next to each other, right? So it's a sequential model. And this has some limitations because sometimes we may have more than one path in the network and we want to be able to have some sort of like multimodal representation and transformation of data. And therefore, in these cases, functional API is a lot more flexible. And the goal is that you can really think of each layer as a function that accepts some input arguments and produces some outputs. And as you can see here, and this is one thing that we're going to implement, is that you can have like two different types of inputs that are provided to your network, and you have different transformations. And eventually we concatenate the result together and provide a single output, like let's say if you have a binary classification problem or a regression problem. So this is a really, interesting topic where you get a lot more flexibility in terms of designing your networks. Okay, so let's get started here. We import the necessary libraries and packages, NumPy, Pandas, TensorFlow, and then from TensorFlow, we import Keras. We are going to run this cell to make sure that we have TensorFlow properly installed, and you can see the version here. So now we want to, first, in the first example, we're going to again work with a synthetic or simulated data. In the next example, we're going to work with a real world image classification problem. But for now, let's look at the synthetic data created using make blobs. And we have the centers for this simulated data set. So you can see we have like 4 centers. And then we want to also assign 2 of these classes into one group and then the other 2 into another group. So this is what we covered last time too. So you can see we create these 4 blobs or clusters, and these 2 belong to the same class, and the 2 off-diagonal clusters belong to the same class. And this is a difficult problem in the sense that this is a nonlinear classification problem, because we cannot just find a linear decision boundary to correctly classify all these data points, right? So that's the code that we have here and what we covered last time too. Okay, so now let's focus on defining a model, compiling, and training, right? So we're going to import sequential model from Keras, and also dense layers, right? So the dense layers are fully connected layers, the one that we already know, the one that all the neurons in one layer are connected to the neurons in the preceding layer. And we also divide the data into train and test sets using train test split. And here we set the test size is 1/4 of the data, and we can define the random state as well. So you can see that in this case, we had 400 data points. If we use 75% for training, this means that we have 300 training data points and 100 data points for testing. And these are 2-dimensional data points, right? So the number of rows is always the number of samples. The number of columns is the number of features. In order to perform a grid search, it makes sense to simplify the process by defining a function that creates a model for us, right? With 2 inputs here. One, the depth or the number of hidden layers, and then the width or the number of units. It's always a good practice to also use docstring to explain what this function is. So you can see that we want to create and compile a sequential neural network model. The number of hidden layers, right, is the number of hidden layers. And here we say that the way that we implemented this, you want to make sure at least you have 1 hidden layer. Otherwise, the implementation that we have here will fall apart, but that's okay. That's what we have explicitly mentioned here. And also the number of units, right? And, as you know, when you define a function, you can always have some default parameters too. So if somebody doesn't define the depth and width, we have 1 hidden layer with 32 units in it. So in order to create the sequential class, as a reminder, you first instantiate this class to create this object, and then you add your first hidden layer, right? So in this case, you have num units as the number of units, and also the input dimension is the input dimension of your data. And here we are assuming that activation is ELU, or exponential linear unit, right? So in this case, this is a fixed activation function. And then for the remainder of hidden layers, we are going to just add this model.add for hidden layer -1 times, because we already added the first hidden layer, right? So we just have to add these hidden layers for non-hidden layers minus 1 time. And the reason that we separated this is because it's always a good idea to provide the input dimension for your network. So I wanted to make sure that for the first hidden layer, I tell what the input dimension is. But from now on, it doesn't matter anymore because now we know that the input to the second hidden layer has these many inputs or dimensions, right? So it's just important to provide the very first input to your network, which is coming from your the number of features of your data set. And eventually we add one neuron in the last layer with sigmoid activation function because this is a binary classification problem, which explains why we are using this binary cross entropy. We are also using a stochastic gradient descent with this learning rate. So right now we are only changing depth and width. So everything else is fixed. And so this will return a compile model. So we're gonna run this cell. So right now we just define everything. And here we perform our full grid search, right? So hidden layers can be 1, 2, 3, number of hidden units, or the width can be 2, 4, 6. And also the way that we implement these is that we define this variable best accuracy, which contains the best accuracy observed so far. And every time that we see something better than the previously seen accuracy, we update this variable. And also we store the corresponding parameters in this Python dictionary, right? So since we have two hyperparameters here, we have two for loops, right, to go through all possible combinations. We print what we're trying to run in each case. We create the model. We fit the model using these fixed hyperparameters. So in general, batch size can be other hyperparameter. So you can see that there are a lot of hyperparameters when you're working with neural networks. And then for the last step, because when you're using model that predict in neural networks, you find probabilities. So you need to now convert this to class labels. So here we put the threshold at 0.5. So if the probability is greater than 0.5, we assume that the class label is 1. And if it's below that, it's 0. And then we define find the accuracy score. And if this is best accuracy, is better than the best accuracy, then we update it, and also we update our best parameters that we have. So this is a dictionary where we want to keep the number of hidden layers and num units. So this is a very simple implementation of hyperparameter tuning, except for the fact that this is kind of a slow. If you want to, let's say, have 10 different hyperparameters, each one, let's say, have 5 or 6 different values, that would be a lot of combinations that you have to consider, right? To be exact, if it's like, let's say, like 5 different values for each, right? So you have 5 times 5 times 5, and you have to do this 10 times, right? So that's something to keep in mind. So let's run this. So you can see that now we are starting with the first model with 1 hidden layer, technically, null layers, and 2 units. So now we're considering 4, 6 units. So you can see that in this case, obviously, for the very first case, we didn't get a great accuracy, but it started to be much better when we went to 1 hidden layer and 4 units. So let's get this done and see what we get at the end. Okay, so this didn't take too long because this is a relatively small and simple data set. But according to what we just saw, it seems that in this very specific case, 1 hidden layer and 4 hidden units is enough, and we get close, or exactly, we get to 100% accuracy, right? So it is true that we have other cases that we got to 100% too, but the way that we have set up our problem is that we are looking at the best results so far. So at some point when we get to 100%, so then we can technically stop our grid search because we got the 100% accuracy, and we do not really want to change that in the future. Although, again, this is a very simple case that we get to 100%, but in many real world cases, we probably never get close to 100%. So now let's make this a little bit more interesting by adding the choice of activation function too, right? So everything is very much like before, except the fact that now we also have activation function, and that's how we provide this input argument here, and we can change this. And remember, for the last layer, the output layer, we have to use sigmoid because that's the one that we use for actually estimating probabilities. So that one should stay sigmoid. But for the hidden layers, because their job is to provide the hidden representation of data, we can use any activation function that we want. And you can see that here we are doing the same thing, except that we are using ReLU, ELU, and swish activation functions. If you want to know the exact implementation and definition, the easiest thing is to go to Keras documentation page and look at what exactly each one means and the exact definition, right? So rectified linear unit has a very uniform definition. It's if the input is positive, we get the same number. If the input is negative, it's zero. That's something very standard. But with the ELU or exponential linear unit or swish activation function, you can exactly see what the definition is when you go through Keras API, and there are a lot other options too. I think about, as far as I know, 17 activation functions that they are already implemented and built in Keras. Okay, so we run this to see what we get here. So something that is very interesting right now, you can see that when we use the ReLU, so the R is here, the ReLU activation function, it seems that we get really low accuracy results, right? It's 0.42, which is really bad, right? Since this is a binary classification problem, meaning that if you use just, toss a coin, and as long as it's a fair coin, you should get on average close to 0.5 accuracy. So this is even below that. That's not great. But obviously, you can see that it gets definitely better when we consider like other combinations of hyperparameters. We do get a couple of cases close to 100% or one, since here we are looking at the proportion of correctly classified data points. And in this case, it seems that we again get 200%, but the number of hidden layers is 1, number of hidden units is 4, and we have to use the swish activation function. Something also I want to here emphasize is that the final accuracy level depends on the number of hidden units and hidden layers, but also depends on the initial solution, right? So that's something we discussed before about the reproducibility. So in these cases, when you're performing a grid search, really your final solution also depends on your initial solution and how the network has been initialized. So that's why if you run this code probably 10 times, you may get inconsistent results. So therefore, if you really want to make this even better, what you really need to do is to make sure that you perform more like a cross validation or do this training and testing, like let's say 10 or 100 times, whatever the number of times that you can afford, and then look at the average accuracy scores. That definitely make your code and your analysis a lot more reproducible and consistent. But here the goal is to show you how you can actually perform hyperparameter optimization. Okay, so now let's look at this image classification problem, right? Using the sequential API, because that's what we already know. And in this case, we are working with the fashion MNIST data set, which is kind of like the handwritten digits data sets, except that now we have these fashion items, right? We have coat, t-shirts, dress, etc., like sneakers, right? And we want to be able to correctly classify these images. So each image is only like one item, and they're relatively small. They're like 28 by 28 pixels, which means that if we vectorize them or flatten them, we have 784 elements. So we want to go through all these steps again, right? Creating model, compiling, training, and evaluation. So in this case, this fashion MNIST is part of the Keras built-in dataset. So you can go keras.dataset.fashionMNIST. And then when you load the data, the nice thing is that this already comes with a predefined training and testing split. So therefore, you don't have to do it yourself. Already has a designated test data set. And then something else also we want to do is to divide the training part of this, that's what I call this train pool, into training and validation set, right? That's important because usually you want to perform hyperparameter optimization on only the validation set, and then use the testing data only once. You see that also here in terms of pre-processing, we are dividing all these X values by 255. And the reason for that is that these pixel values are from 0 to 255 is a grayscale image. And so it is nice to normalize this. So make sure all the inputs are from 0 to 1. So we don't have to deal with gradients that they become too large throughout the training process, right? So that's a very common technique to use when you're doing any kind of image processing to make sure that none of the inputs are too large or, on the other hand, like too small, right? So you want to have a nice range, like 0 to 1, it's typically considered very much acceptable. Okay, so I forgot to run the previous cell. I need to do that first and then run this cell here, right? So you can see that very similar to MNIST data set. This has 70,000 images. We use 60,000 for training. And remember, for the training part, we have to keep 5,000 here according to what we have for validation and then remaining for training. So in that case, it would be 5,000 for validation, 55,000 for training, and 10,000 for testing. And you can see that also these are the labels that we have here, that they're unsigned integers, so we don't have to do further processing on this because these are already integers. If they were like a strings or something like that, we had to do further processing. And also you can see here, you can use np.unique with return counts true. So this shows that we have these 10 classes, and each class we have about 5,500 data points, right? So it's a very fairly balanced data set, and this is one of the things that makes this a little bit easier compared to some other problems where you may have like class imbalance. And let's look at one of these images and see what we get. And you can see that here, for example, we have that I believe like it's called boot in the data set, or sneaker, sorry. It seems like this is the sneaker class. Now we can create the model that we want to have. So in this case, we are using in the sequential class. We instantiate this, we create this object. Now we have to add our hidden layers. But something also remember here, before adding hidden layers, we have to flatten this 28 by 28 image. So that makes sure that it's a vector of 784 elements. You have to do this because these dense layers, they work with, with one-dimensional kind of like arrays. So that's why we have to first flatten. This obviously doesn't have any parameters, this layer. It's just making things flat and vectorize. And then we add two hidden layers, one with 300 neurons and the other one 100 neurons. And we use the ReLU activation. And then in this case, because it's a 10 class classification problem, we use 10 neurons and we use the softmax activation function. Another way to create this model is to just provide a list of layers, right? So you can use model.add every time you want to add a layer, or you can just, give a list of all the layers, and this is exactly the same thing as what we have done before. It's always a good idea to look at model.summary to show you what these, the dimensionality of data is. So you can see that we have these 784 dimensional inputs, and then we go 300, 100, and in the last layer, each one is represented by a 10-dimensional vector. These are the estimated probabilities, right? The probability that that data point belongs to one of the, to each of the 10 classes. And if you're wondering why we have this none here, so this none here corresponds to the batch size, meaning that the number of samples we have in each group or batch when we fit this to the network. And this does not really matter at all right now, right? So the dimensionality part is important because that's what we are trying to change. But if we, like, let's say, fit 10 data points to our network, at the end, we also get 10 of these 10-dimensional vectors. So the the input part, the batch size doesn't really matter, and that's why, it's totally fine not to define that and let it be as none, meaning that we don't know right now. And still, your like model here, you can see that we can find the number of parameters that we have, right? So these are the number of parameters needed to go from this 784 dimensional input to a 300. And if you're wondering how we can actually calculate these, so the way that we defined the weight matrices when we talk about the math behind neural networks, you know that you have to multiply these two numbers, except the fact that also you have a bias term. So that's why you can always add a 1 to this preceding layer. So think of this as actually a 785 dimensional input, because you also have that fixed bias term. And then you multiply that by the number of neurons in the next layer, which is, this 300. So if you do the math, right, so 785 by 300, 301 by 100, and 101 by 10, you should be able to get exactly the same number of parameters. So this is a nice way of checking your model to make sure that this is actually consistent with what you think you are implementing. The other nice thing is that you can also visualize your model. So you can do this using keras.utils plot model. So you can see that, you have your input layer, right? And then you flatten this, and then you have a dense layer, another dense layer, and then finally your output layer. So this is a very nice way of actually understanding a very nice visual representation of your network. And that's also something that I believe we mentioned this before too. You can also name the layers too. So in this case, since we only have two hidden layers, technically, it probably does not really matter as much. But you can also name each layer, so you know that when you want to, if you want, for example, know the weights or parameters for each layer, you can easily find this information later on, right? So that's the only thing we added here. And so in this case, when you use this plot model from keras.utils, you can see that now these are more meaningful, right? So you have hidden one, hidden two, these are the names we provided, rather than this naming system that is part of keras. And you can look at these layers. So you see that when I run model.layers, so look at the attributes here. I can see that I have all these layers here. Remember, the first one is the flattened layer. And this is not very useful right now because this shows you the address in the memory where these layers are saved. So this doesn't give us much information, but you can actually look at any information you want about this, right? So let's look at the layer.name, right? The name of the layer. So you can see that now we go through that memory address and look at what the name of that layer is, right? Or there's this method called get_weights. You can find the weights and biases, right? So as we said, it's 784 by 300, and then we have the bias term, right? So we have 300. So if you add all of these, it's technically 785 times 300, right? And then since here we have a multi-class classification problem, we are using a sparse categorical, and a sparse is because here we have these labels in the form of 0, 1, 2. If you're using one hot encoded representation, then you don't have to use this sparse categorical cross entropy, and you just use categorical cross entropy. So it really depends on how you provide the labels. When they're in the form of integers, like what we have here, you have to use the term sparse, right? That's what it means in this context. And other than that, you just define your optimizer, the metrics you want to have, and then we use model.fit to train this model. We provide the training data. And here you can see why we divided the data into train and validation, right? Because we want to make sure that we measure both the loss and validation and accuracy on the validation data to make sure that the model is not overfitting or underfitting and so on, right? So you don't want to use your test data here because you only have usually the right to use that only once. So in this case, you want to make sure that whatever training data that you have, put aside a portion of that for validation purposes. So here to see, we get the information, right? So we have the loss on the training data, accuracy on the training data, and then the loss and accuracy on the validation data. That's why it starts with VAL. And you can see that overall, the validation accuracy is converging about like, 0.84. The same thing with accuracy, we are getting to the same level. So this means that this model, at least right now, with this number of epochs, is not doing like overfitting or any of those problems. And if you're wondering why we have 860, iterations or updates per epochs, that comes from the fact that we put the batch size to be 64 here. And because of that, we have 55,000 data points. So if we divide them to groups of 64 data points, we end up with 860 sort of like updates or iterations per epoch. And now we can look at the history. That history, create a data frame, and plot these to even better visualize the performance of our model. So you can see that the loss is going down. That's great because loss hopefully should get closer to zero. And the accuracy is increasing over the number of epochs. So that's great. And also, if you want, you can use model that evaluate, provide your testing data. And in this case, you don't really want to do this in multiple batches. You can just say that, okay, I have a huge, batch size, meaning that find the values of the y-test for all the input testing data points rather than doing this in smaller batches. We are not really finding gradients or anything like that right now. So even if, for the data of this size, you should be able to provide the whole test set in one batch. And you can see that, we get close to that 0.83 accuracy, which, this is what we expected given that validation and training data were consistent. And in this case, for example, you can look at the estimated probabilities for the first 3 test data points. So that's why this is 3. And then we have 10 columns. So each column corresponds to the probability for each class. So you can see that for the first test data point, and remember, here we have 10 classes. We are, 56% chance that it belongs to the last class. And, there's 30% and 13% chance belongs to the other classes too. We are way more confident about the second testing data point, right? So that's the one that is 97%. And for the last one, we are very confident that belongs to class 2, right? So this is the first class or class 2. So that's, how we can find this. And if you really want to capture this, you can use like argmax and make sure that the axis is equals 1. So in this case means that go through each row and see where the location that the maximum occurs, right? So this location is 9, this location is 2, this location is 1, right? So if we assume that the class labels that start from 0, these are exactly the class labels that we have for each testing data points. So my recommendation is to visualize some of these testing data points and then look at the class labels and see whether they are consistent or not. So that would be a really nice exercise. Okay, so now let's talk about functional API. So as I said, the functional API, the nice thing is that each layer is exactly like a function, right? So you can provide an input and that layer produces an output. And in this case, usually you want to also explicitly define your input. So you say like input, this is the shape of the input that I have, right? And then this input goes to the, like, let's say first hidden layer, which has the one that has 128 hidden units. And this is the result. And then this will be fed to the next layer, right? And the only main thing here is that at the end, you have to do model declaration, meaning that you have to use this model and say, what are the inputs to your model and what are the outputs, right? Because all the intermediate, computations are already defined. But what you really want to know is what the inputs are and what the outputs are. So let's go back to some synthetic again data here. So in this case, we have a 3-class classification problem. These are the centers, and these are the like the covariance matrices for each 2-dimensional data, right? So if I just plot this data, you will see that we have these 3 kind of like mixtures of normal distributions, and these are multivariate. So you can see that we have the centers, we have covariance matrices. Like always, we do our train test split, right? So that's something important to do to make sure that we have some training and some testing data. But once you want to define your model, now we are going to use functional API, right? So you say that input. So this is my input. The input is of size 2, meaning that you have a two-dimensional data. We can name the layer 2, but now these inputs will be given to the next layer as the input, right? Exactly when you write a function f of x, that's your x right now, inputs. Now you define your layer, and that will be the output, and the output here goes to the next layer. And in this case, since we have 3 classes, right, so we put 3 neurons, and we use the softmax activation. And eventually, you have to tell Keras that what are the inputs and what are the outputs. So the inputs, in this case, it's easy. It's just this one, inputs, and the outputs is this one. And this underscore here, you see, doesn't really matter. It's something you're allowed to use. So in order to make sure that I'm not using the same name as the name of the input argument that I have to provide, I use this underscore. But really, if you remove this, it should work. But it's a common practice sometimes in programming to put these underscores to make sure that we differentiate between different variables. And in this case, also, I'm using this, setting the random set for Keras. And then what I really want to do here, if you look at like what we have done, the only input is this choice of activation, right? So we want to see if we have the same network in terms of depth and width, how much do we get different results if we change the type of activation, right? So here we have 3 choices: soft plus, ELU, and ReLU, right? And we want to see what results we get, right? So in this case, we create our model, we compile it, we train it for 40 epochs, batch size, and we want to see what kind of result we do get for each activation function. So you can see that if we use soft plus in this case, we get 0.45 accuracy. And this is not actually like super bad, because remember, here we have 3 classes. So if you do a random sort of like, guessing in this case, you should get closer to 1/3, which is like 33%. So still 45% is above that. You can see that with ELU, you get 70%, and ReLU, you get about 64%, right? So this happens when you use these individual activation functions. But now, in order to understand why functional API is useful, let's see if we can actually define a network which uses all these 3 activation functions, and we concatenate the result, right? So one of the nice thing about Keras is that we have this concatenate layer, and this allows us to combine or merge multiple inputs together. And this is something very useful when you want to build complex models. For example, when you have multiple inputs, multiple branches, and so on. So what we do here, so if you look at it, like we define our input layer, and then we provide this same exact input layer to 3 hidden layers, each one with one of those 3 activation functions, right? ELU, soft plus, and ReLU. And the inputs are the same. Obviously, the outputs are not the same because you're using different types of activation functions. We name them as branch 1, branch 2, branch 3. And then what we do is we use that concatenate layer, right? So now we have these 3 branches. We want to merge and concatenate them together. So this is very much the idea of vectorizing things, except that now we are putting 3 different vectors together to form a larger vector. And now we provide this concatenated layer to the output layer, which has 3 neurons, because it's a 3-class classification problem. And we should use the softmax, right? That's something that we have to use softmax because we want to have estimated probabilities. And eventually, we want to also say that what this model accepts as inputs and outputs. And we do the compile and feeding and evaluation. So in this case, we only have one model, right? So we have one model which has 3 branches, and each branch corresponds to 1 activation function. So you can see that here we get 85% accuracy, whereas before, the best accuracy that we had with an individual activation function was 71%. So in this very specific case study, this does not always happen, but you can see that combining all activation functions by having these branches in your network it really helps to improve accuracy, right? So we got from 71% best accuracy to 85% total accuracy. And all this happened because we have now these different branches. I actually have to change this to 3 branches. I don't know why it was 2. So we want to create 3 branches with different activation functions. And I have to change 3 here too. Okay, so the story what we learned here was that, well, the choice of activation function is very helpful, right? We use only one type of activation function and we got lower accuracies. Then we combine together and we got much better accuracy. So now this is the part that we want to answer, and this is one of those like more like modern topics in neural networks, is that can we move beyond fixed activation functions, right? The activation functions that they always have the same behavior in the network, and be able to adapt that to what the network really needs to get the best out of the data set that we have. And this is the idea of introducing trainable parameters into activation functions. And in order to kind of like, understand this, let's look at a little bit like a different data set. In this case, we are looking at the iris flower data set. This is something that we saw when we talk about logistic regression. So you can have access to the input features and outputs. If you want, you can standardize the data too by using this standard scaler, and then we do train test split. But the part that is new here is this part. So what this part says is that we want to define a new class, right, which we call a custom activation. This class inherits from the layer class from TensorFlow, right? So that's why object-oriented programming is very important, because you can inherit properties from a bigger and probably like more complex class. And now we need to have 3 things here. The constructor, which means that we want to initialize things here. And in this case, because we're only adding 1 parameter to the activation function, we set this unit to be to 1. And then we have to build. So in this case, we want to define what that trainable parameter is. So we use this self.add_weight in TensorFlow and Keras. So this is saying that we want to define an activation function that has this parameter, that this parameter or weight is not fixed, it's actually trainable, right? And then we have to provide the shape of that, which in this case is just 1. And the most important part is here, you have to put this trainable parameter set to be equal to true, right? So this means that, okay, now we're adding this trainable parameter. And this allows you to build your model, right? So in this case, this means that, okay, now we're just adding this extra parameter to whatever other parameters that we have. And now the third thing is to change this or define this call function or method. And this is what exactly tells us how this activation function looks like, right? So this is the ReLU. And instead of just having ReLU of X, now we have ReLU of alpha times X, where alpha is trainable, right? So you saw that we added these extra parameters to the rectified linear unit function, and we are telling TensorFlow and Keras that this is something that is trainable. So why we exactly, only change these 3 things here is something the documentation page. If you go to more advanced topics, that is on the Keras API, they explain, how to, define our own or custom activation functions. But the idea is that we only have to define the forward pass, right? Meaning that how we want to use this alpha to define a new activation function. And after that, everything else, including the back propagation and finding derivatives, they're handled automatically in the background. So we don't have to be worried about them. So this is what, in general, this call is what TensorFlow and Keras they use, right? So they use call to define the forward pass. And build is usually to, as the name suggests, to build your model, understanding like what parameters you have and what are the input shapes are, etc. Okay, so now that we define this class, and if you need to use this anytime during this class, you can just copy paste this and just adjust mainly this call part of it, because that's the one that usually is different. The one that, for example, you may want to add this alpha to soft plus or some other activation function. So after this, now we do very much like we did before, right? So we define a sequential class here. So we don't need to always use functional. In this case, we use sequential. We add our hidden layer with this new activation function, right? So if you want to call this or create an instance of this activation function, we just have to instantiate this and provide this number of units. And in this case, you can see that now for the last layer, because we have a three-class classification problem like before, we are adding 3 neurons, and this is the activation function softmax that we are using. So in this case, we're using really like one hidden layer with 32 units and this custom activation function that we have here. And now we do the training and defining our optimization technique, compiling, so everything else that we have seen before. And the main thing is to just measure the accuracy here and see what we get in terms of the accuracy of our model. So you see that here we get some warnings that you can ignore. And you can see that in this case, we get actually 100% accuracy, right? Using this custom activation function and this one hidden layer that we have here. And if you want to do that now, like the summary part to see like how this model looks like, you can see that, right? So these are the number of trainable parameters that we have. And remember that in this case, that alpha of the ReLU is also one trainable parameter. And if you're wondering what that value exactly is, here is this one, 1.73, right? So we can go through the weights of our model, right? And look at the one with index 2, and you can even see here that it says that this is the alpha, right? So you can actually see the optimal value of that parameter that we have added. So that's like the really interesting part about these libraries, that we get a lot of information. And now let's do the same thing now without a custom activation function, right? We just use ReLU, right? This means that in this case, that alpha parameter is just equal to 1. That's the, because ReLU of x is technically ReLU of 1 times x, right? So if you want to parameterize that, you can think about that alpha being 1 here, whereas in the custom one, alpha is something greater than 1. And if you run this, we will see that we get about 96.7% accuracy. So again, the difference might not be huge since this iris flower is a small data set, but this is definitely something that can be added to your network if you're really trying to improve accuracy and you think that the existing model is not performing as it should. The last thing we want to cover here is this idea of functional API and having, again, multiple branches. And one of these is known as this wide and deep learning. So why is this thing called wide and deep learning? Because let's say you have a problem where you have inputs, and some of the input features that you have, you think that they are very important and they should be included in the final output layer. And there are some other ones that you think that they're not, automatically should be there in the last layer, and there should be some transformation of these inputs. So in this case, you can actually explicitly define these so that part of your input features do not go through any major transformations and they can get to the output layer, and some other ones they can go through more transformations. This is also helpful if you have multimodal data, right? So you have a data set where some inputs are tabular, some inputs are images. So for the images, you want to like reduce their dimensionality, do some transformation, but for the tabular data, you do not want to do that, right? So this is the idea of wide and deep learning. And you can see that you can do this very easily using this, functional API that we have. So here we are working with this built-in scikit-learn data set called Fetch California Housing. Obviously, you can find more information on the scikit-learn. We are gonna look at the layers that we need, input, dense, concatenate, and we're using the functional API here. So therefore, we have to use this model from Keras. This is the one that allows you to define explicitly what the inputs are and what the outputs are. Very similar to other scikit-learn data sets, we import this data. We look at the input features and outputs. You're more than welcome to do some exploratory data analysis here, but since we have some outliers in this data, I only work with outputs where this y variable is less than 4, right? So that's something that I do here to make sure I don't have to deal with some of the extreme values. But, again, that's something you can do more exploratory data analysis if you want to. And we do also standard scalar here. So in this case, you can see that, like, when we look at this index or IND here, we have these false and trues, right? So the ones that they're, less than 4 the output, and the one that they are not. So we want to make sure that we only keep the ones that are less than 4. And therefore, overall, you can see here that the training data set that we have about 15,000 data points. So it's a relatively nice data set. So here's the part that is very important about this specific problem, right? So you can define the shallow part and then the deep part. Like the shallow part means that these are the inputs you think are very important. You don't want to do many transformations on them. And in this case, we assume that these are the first two input features. So here, if you look at this second dimension is 8, meaning that we have 8 input features. Let's say here, hypothetically for the first two input features, you don't want to do much transformation on them. And the remaining 6 ones, you want to send them through a deeper network. Therefore, in this case, we say that we have an input of size or dimension 2, and this is called a shallow input. And then this one, right, the shallow input goes through this hidden layer and with one neuron, right? And also linear activation function, right? So we find a weighted sum of these two inputs. We, find a scalar, and this is our shallow output. Now, let's talk about the deep part. So in this case, we have the input, which is of size 6 because we have 6 input features. The rest of these, 8 features that we have here. So the first 2 ones are in the shallow. The remaining 6 ones are in the deep part. And this one goes through like deeper transformations, right? So you can see that our deep input goes into this hidden layer, and the same the other hidden layer, and finally this output layer. And now we do the concatenation part, right? Like we have two different types of outputs, shallow output and deep output. We concatenate them, and eventually we send this to the final last layer that we have, or output layer that we have. And since we want to predict something that is a scalar, so we only put one neuron with the linear activation function. And here you see why that model that we imported here is very important, right? Because now we can say that, well, we have two inputs, right? The shallow input and the deep input. And now we have one output, which is this output that we have here. So here we are saying that we have two different types of inputs. And you can see that now we can look at even like the number of parameters. Now this becomes even more interesting, right? So you can see that we have the case that we have the deep input. These are the transformations on that. And then we have the shallow output, like the deep output. So these are each of dimension 1. We combine them, so that'll be dimension 2. And eventually we have a scalar, which is the final output that we have. You can also use the plot model here to get a nice representation of these. So you can see that the deep input goes through these two hidden layers. The shallow input is different because it gets directly connected to the shallow output. And that's how this wide and deep model works. So once you also want to do model fitting, you need to make sure that now these inputs are separated from each other, meaning that the first two input features are the first input. So this is a shallow input, right? And then the remainder are like the deep input, right? So make sure that you do respect the way that you define the inputs here, right? So here we said that the inputs are given in this form. So it's a list where you have shallow input and deep input. And that's exactly how we provide it. And 20 bucks, batch size 64. So you can see that after 20 epochs, these are the values that we get here. And one of the things that you can do in this case, you can plot the predicted values versus the test values. So if I run this cell, so you can see that on the x-axis I have the true values. Remember, I cut everything to be less than 4. And then we have the predicted values. So hopefully if we have a perfect classifier, everything should be on the 45-degree line, because the true values and predicted values are exactly identical. But again, it's the real world data. Probably that's not going to happen, right? So you can see that we have this scattering around 45-degree line. But the good news is that it's somewhat symmetric, right? So it doesn't have necessarily a clear bias towards one direction, which is very helpful. And as you can see here, still you can use metrics such as like mean squared error, mean absolute error. So those are all like ways of summarizing the performance using a single number. But if you really want to see the overall behavior, this is what is known as the parity plot, which is very helpful in the sense that you can really look at the behavior of your model in terms of its overall performance.